Hi budding engineers, welcome to Structure Engineering Lectures and welcome to the new playlist on the design of steel structures conforming to IS 800 2007 limit state method. In today's class we shall see the design of gusseted base. Right? These are the designs of the column bases. One problem with the bolted connections like this even in the previous class we have seen the design of the column bases, slab bases like this, right? Wherein we have seen both the bolted as well as the welded connections. I hope you are enjoying the discussions. If you are really enjoying the discussions, don't forget to click like, share, subscribe to our YouTube channel. Now let's see the brief profile of the speaker. That is I, Dr. D. Rupesh Kumar, obtained my BTech in civil engineering from Nagar University in 1994, MTech in structural engineering from JNTU Hyderabad in 2000, and PhD in structural engineering from JNTU Hyderabad in 2009. Presently, I am working as a professor of Department of Civil Engineering, University College of Engineering, Osmania University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement, concrete designs, steel structural designs, structural analysis, entitlement analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 research papers in international as well as national journals and conferences, organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, and delivered 13 guest lectures and edited 2 books, supervising 14 PhD research scholars and supervised 30 ME theses. I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 plus designs of the RCC, steel, composite, low-rise, high-rise, multi-story buildings, as well as road and rail bridges. Now, before we see the actual discussion, student, let us see what we'll be seeing in this today's class. We'll be discussing 2 problems like this. Right? One is that of the design of bolted gusseted plate, wherein to I section what is attached is a gusset plate and a gusset angle, right? However, even we can also attach a web clip if it is subjected to some nominal bending moment about the weak axis. Now we can see that these are attached about the major axis, right? Generally these gusseted bases are generally used if at all there is a heavy load need to be transferred by this column to the slab base, and if there is a movement about either the strong axis or that of the minor axis, major axis as well as the minor axis. In such cases only we will be providing the gusseted bases. Otherwise, we will just provide the slab base itself. The other day we have seen that, right? You please revisit, right? However, the slab base will be resting on the concrete pedestal, right? Now, let us see that is the front view of the same, right? Base plate, and this is a gusset angle and gusset plate, and this is a I section, and this is the plan. I section is attached with a gusset plate and as well as a gusset angle on each of the flange, right? And this is what the side view, wherein the gusset plate which is attached to the flange of the column is varying width from here to the equal to that of the width of the base plate, right, or a slant height or a sloped height, right? And it is connected by means of the bolts, right? Now even we can see here this is a gusset angle in side view, right? This is another schematic of the same, right? This is the gusset plates. Brown colors are the gusset plate, and this violet color is that of the gusset angle, which are connected by means of the bolts on each of the flanges, right? This is an I section, right? And we can see the same side view. Just have shown in the schematic, right? I section flange is seen to which the gusset plate is attached, and over which this is the gusset angle will be attached, right? Therefore, this will be stiffening this lower part so that this will take the bending moment about this strong axis, right? And the same I am showing in 3D view, right? This is an I section. This is a compound built up section where this is even provided with a cover plate, I section with cover plate, which are already welded in 2 rows, and this is provided by means of this cover plate is indicated in blue plate, student, right? And the gusset plate is shown in yellow color, which is attached to the flange, and at the bottom what is also seen in green color is gusset angle, which are connected to the flange by means of the bolted connections, right? We can see they are provided in two rows. Even for the gusset plate also, they are provided in two rows, right? And this gusset angle is anchored to the pedestal through the base plate. The base plate is seen in the pink color. Pink color. We can also see to the web also a cleat is provided, which is also provided by means of just two nominal 216 and 216 bolts, so that even if any bending moment about the minor axis, that will also be taken care. Right? This is a 3D view. Right? Let's see a numeric problem. Two numeric problem, student. Right? Let us move to the problems wherein this is the very first problem. A column ISHB. This is a problem of bolted gusseted base problem. Bolted gusseted base problem. Right now, let us see this numeric problem. A column ISHB 350 at the rate of 661.2 Newton per meter carries an axial compression load of 1700 kilonewtons. It's a Audi factor load, right? Design a suitable bolted gusseted base, means slab base as well as the gusseted plate as well as gusseted angle. That is what called the gusseted base system, right? Use M15 grade concrete for concrete pedestal and use 24 mm dia ordinary black bolts of grade 4.6. Ordinary black bolts of 4.6 grade, right? Now, that is how the problem given, student. Now let us see the given data. Now if I go to IS 800 2007 table 46 page number 138 for ISHB 350, let me go to that ISHB page number 138, right? ISHB 350 at the rate of 67.4 kg per meter. Now I am just noting down the relevant properties, that the depth of the section is equal to 250 and the width of the flange is equal to 250 and thickness of the flange is equal to 11.6 and thickness of the web 8.3. Therefore, once I note down this relevant data, right, here just have noted that relevant data, right? Now I'll also go to the other data, that steel use what is also given in the problem, that use Fe 410 grade steel. There is a data given, right? And so for that, now we can say that the steel ultimate strength of the steel is equal to 400 Newton per mm, 410 Newton per mm square, and the yield stress of the steel is equal to 250 Newton per mm square. And let us also see the bolt data. Now what is given is that ordinary black bolts of 4.6 grade bolts need to be used. Therefore, now from IS 800, now I have the ultimate strength of this bolt 400 Newton per mm square, as well as the diameter. The diameter is also mentioned as 24 mm. Nominal diameter of the bolt is equal to 24 mm. Therefore, if I go to this table 19, page number 73, let me go to that page number 73 at a quicker pace. Right, page number 73. 73. Yes. Therefore, there now I am having the diameter. The diameter of the hole, right, is 2 mm. If at all it is 24 mm, and larger than 2 mm, 24 mm, it is 3 mm, right? 3 mm. And also the other specifications are like this, that the minimum spacing from class 10.2.2 shall not be less than 2.5 times the nominal diameter of the fastener, as well as the maximum spacing shall not be more than 32 T or 300 mm, whichever is less, right? However, even these specifications are applicable, right? This maximum pitch should not be more than 16 T or 200 mm, whichever is less for tension members, and 12 T and or 200 mm, whichever is less for compression members. Generally, now we are designing a compression member, therefore 12 T or 200 mm is the maximum spacing. And the other specification is that of the edge distance, right? Edge distance. The maximum edge distance shall be taken as 1.5 times the hole diameter. In case of the machine flame cut or sawn or planed edges, right, like this. Therefore, using this data now, let us substitute into this. Now from this table, now I do have hence the diameter of the hole, right, 24 plus 2 is equal to 26 mm, and the edge distance, just now we have seen that edge distance is 1.5 times the diameter of the hole. Diameter of the hole is equal to 26, therefore it now works out 26 multiplied by 1.5 works out at 39, and as well as the pitch of the bolts. Pitch of these bolts is equal to 2.5 times the nominal dia, therefore 2.5 multiplied by 24 or say 60 mm. 60 mm. We'll be using the an edge distance of 39 mm as well as the pitch of 60 mm for our designs. Right? Now, also I require the net area of the bolt. Therefore, if I go to IS 1367 part 3, 2002, page number 9. Let me go to the page number 9, student. Right? Now, I do have, yes, from this for M24, M24 means diameter of the nominal diameter of the bolt is equal to, for that now the net effective area is equal to 353. Or even if you don't remember this, what you can do is you may take approximately equal to 0.78 multiplied by the gross area pi by 4 multiplied by 24 square. Both of these give the same result, 353 mm square. Therefore, that is how. And also another data is used, the grade of concrete as M15 means FCK is equal to characteristic compressive strength of the concrete is equal to M15 Newton per mm square. 15 Newton per mm square. This is how the relevant data, student. And once I note down the data for this M15 grade concrete, if I go to, then what is the bearing strength? The bearing strength, right? Therefore, now I'll initiate the designs first, right? The first building is the design of the gusseted base. First, I'll design the gusseted base. Then I'll go to the bolted connections. Right? Therefore, now if I want to design the gusseted base, then what is the bearing stress of M15 grade concrete as per IS 456? Let me go to this page number 66, the class 34.4, IS 456, yes, and then IS 456. Now code says that for limit state method of design, the permissible bearing stress shall be taken as 0.45 FCK. However, as per IS 800 it is a 0.6, therefore 0.6 FCK is more than 0.45. I am not taking that, hence I am taking as per the IS 456 as the value 0.45 multiplied by 15. It now works out, say that W is equal to RFB is equal to 6.75. Hence the bearing area of the base plate required, A is equal to the factored load P divided by the bearing stress 1700 multiplied by 10 to the power 3 divided by 6.75. Now I require 251 multiplied by approximately 252 10 to the power 3 mm square, 10 to the power 3 mm square. Therefore, once I get this, now what I'll do is I'll propose the base plate like this. Right? I'll propose the gusseted base or the slab base, gusseted base like this, right? Then assuming 60 mm gusset plates and two flanges of the column section, two angles of ISA 150 by 115 by 10 mm as shown in the figure. Therefore, this gusset plate is assumed as 60 mm thick. This is my assumption, right? As well as this angle, gusset angle, is assumed as 150 height, right? And 115 is the width, right? And its thickness is equal to 10 mm, right? Therefore, with these assumptions, now I have already shown the schematic also, right? The schematic in elevation, right? And so the minimum width required for the gusseted base is equal to this 350 mm, right? Plus 260 mm that of the cover plate, the gusset plates, and this 115 plus 115, this 115 plus this 115. This is the minimum width required. Therefore, it now works out, say 612 mm at least, right? Or say more value means 620 or 630 as appropriate. Now I'm saying 620. Therefore, I'm fixing this width as 620 mm for this gusseted base, right? Gusseted base. Once I fix this width, student, then the projection of the base plate from the end of the flange or from the toe of this gusset angle, right? Therefore, what is this projection? this projection is equal to that 620 minus 612 divided by 2. Therefore, that now works out say 4 mm, right? 4 mm. That is how 620 minus 612 divided by 2 is equal to 4 mm as shown in this figure. Means this is from here to here it is 4 mm and here to here this is 4 mm, right? Once I get this, now what I'll do is, hence the width of the base plate required is equal to A required divided by length provided. Therefore, 251.85 10 to the power 3 mm square divided by 620. It works out say approximately 406 mm, but will provide say 410 or more. Therefore, hence provide a base plate of 620 length by 410 mm width, 410 mm width as shown in the figure, right? That I already shown this. This is 620, and in plan even if I see in the side view, its width is equal to 410. That is how the dimensions are fixed. Now we have fixed the size of the base plate, right? Now next I need to next subheading is I need to fix the thickness of the base plate also. I need to fix the thickness of the base plate. Therefore, now what I'll do is, next subheading is thickness of the base plate. Therefore, for getting the thickness of the base plate, now what I'll do is what's the actual bearing pressure under the base plate, right? On the concrete pedestal, right? This is a base plate, therefore this is a concrete pedestal. Hence that actual bearing pressure W is equal to actual load, factored load 1700 divided by 1700 10 to the power 3 divided by actual area provided is equal to 620 by 410. Hence it now works out say 6.68 student, which is much less than the permissible value of 6.75. hence it is okay. If it is not okay, then obviously you need to increase the size of the base plate, so that this is less than the permissible value. Now I am okay in that check. Hence once I get that, now I'll say the length of the base plate acting as cantilever at section XX, right? Let me show, right? Because this is that net cantilever projection. Or let me go to this schematic also, right? Let me go to this schematic, student, right? Just wait for a moment, I'll show. Right? Yeah, this is how. Yes, this is that section at which the maximum bending moment will be there. Therefore, this is that total width minus this to this width divided by 2. Therefore, now I'll do because here the cantilever bending moment, this overhang cantilever distance is equal to how much, right? The distance I'm calculating as say that distance C is equal to 4 mm is the end, right? Plus 115 mm minus this 15 mm thickness, right? Therefore, this is 4 mm, this is 115 is up to the end of this one. Therefore, from which I'll deduct this 15 mm. Therefore, now it works out say a value, right? 104 mm. Sorry, student, right? The thickness of this angle is equal to 15 mm. It is not 10 mm. I'm sorry, right? Therefore, this thickness is equal to 15 mm, right? Therefore, now I'm getting that cantilever projection as 104 mm. Hence, the maximum bending moment is equal to W C square by 2, right? Therefore, substituting which now W is equal to 6.68 multiplied by 104 whole square divided by 2. That works out say a value 36,125 Newton mm. However, if I go to this IS 800 2007 class 8.2.1.2 page number 53, let me go to the page number 53 of IS 800, page number 53, right? Just wait for a minute, 53, right? And so, now what the code says, this is actually for the plates are that of the beams which are under bending, right? Therefore, the fact MD, the design bending strength MD, which are under bending, either that of the plates or that of the slab bases or the beams as appropriate. MD is equal to beta B multiplied by ZP Fi divided by gamma m naught. However, code says that in order to avoid irreversible deformation, under serviceability loads, please make a note, right? MD shall be less than 1.25 multiplied by Fi multiplied by Ze divided by gamma m naught in case of simply supported beams or plates, right? and it should be 1.5 Fy Ze divided by gamma m naught in case of the cantilevered beams or the plates as appropriate. Therefore, however, because now we are assuming it to be simply supported between the two anchor bolts, hence 1.25 Fy divided by gamma m naught. Therefore, recalling that now I do have I would have the design bending moment due to the base plate and the angle both put together. Please make it right is equal to 1.2 Fy divided by gamma m naught multiplied by Ze, substituting numerical values 1.2 multiplied by 250 divided by 1.1 for the base plate. Yield stress is equal to 250 divided by 1.1 multiplied by, obviously, for all the designs we will be assuming 1 unit width of the base plate. That 1 unit is equal to either 1 mm or 1 meter or 1 inch 1 unit. Therefore I am assuming 1 mm for 1 mm base plate. What is that cantilever bending moment that I am calculating, right? Therefore B T square, where Ze is the elastic section modulus, which is nothing but B T square by 6. B is equal to 1 unit, just now we have assumed, right? And let Ts be the thickness of the base plate. That divided by 6. Therefore it works out say 45.45 into T square Newton mm per mm width. Please make it. However, for equilibrium, the factor moment must be equal to design bending moment. Therefore, equating both of these, now I get only unknown is equal to thickness of the base plate is equal to obtained as 28.19 mm. Right, 28.19 mm. However, please see that this is including the thickness of the slab base, right? Hence, now the thickness of the slab base is required. This slab base is required is equal to this 28.19 total thickness, from which already angle is already having like this, right? This angle is already having a thickness of 15 mm. If I deduct this thickness of the 15 mm, therefore what is the thickness of the slab base required? It's equal to 28.19 minus 15 mm. Therefore, say approximately it is 13.19. However, let us say the thicknesses that are available is 16 mm. I am saying 16 mm. However, this 13.19 should be greater than the thickness of the flange. Just now we have seen for the column section, thickness of the flange is equal to 11.6. Therefore, it's already okay. Therefore, let us say instead of 13.19, or say 16 mm, and providing a base plate of 620 mm length and 410 width and 16 mm thick, as shown in the figure, right? As shown in this figure. Now, this is what the base plate, student. Let me show this, right? This base plate design is not just over, right? Or this base plate, right? Now, we have already deducted this. Actually, I got overall thickness, from which I have deducted this 15 mm thickness. Therefore, now just now I got 13.19, or say this 16 mm, right? Once I conclude that, now I will go to the design, other designs, right? This design of next heading is design of the bolted connections. Therefore, by this time I already concluded one design of the base plate is over, and also design of the gusseted plate, which already assumed as per this assumption. 16 mm thick gusset plate was already assumed, and even this gusset angle 150 by 115 by 15 is also over. Therefore, now once I conclude this gusseted base design, now I'll go to the connections, right? The connections are done using the bolts, hence the design of the bolted connections, right? What is given in the problem is that the bolts are the ordinary black bolts. Hence, now if I go to IS 800 2007 class 10.3.3, page number 75, let me go to that, right? Page number 75. I don't have these code specifications, right? Page number 75. Yes. The shear capacity of the bolt VDSB is equal to VNSB divided by gamma MB, where VNSB is equal to FU divided by root 3 NN multiplied by A and B, right? And the bearing capacity of the bolt is equal to VDPB is equal to VNPB divided by gamma MB, where VNPB is equal to 2.5 kb dt fu, where kb is the least of the 1, E divided by 3 naught, P divided by 3 naught minus 0.25, FUB divided by FU, and fourth one is 1. Therefore, knowing these values, now let me substitute into this formulae as per the IS 800, right? However, we can see that let me go to this schematic, right? I'm connecting these bolts, even you can see here actually between the flange and the gusset plate, there is only one weak plane, therefore it is under single shear, right? Like that, even if I see the gusset plate along with the gusset angle is acting as if one unit. Please see, because this is a gusset system which is having still only one weak plane. Therefore, here at this black line only is only one weak plane. Therefore, it is under single shear. It is not under double shear, student. Don't say this is one weak plane as well as second shear plane. That is wrong, right? Therefore, only this black line is the only single shear. Hence, the strength of the bolt in single shear. I know this formula that just substituting into that formula n is equal to 1, right? And this net threaded area of this bolt is equal to 353 that multiplied by FUB is equal to 400 divided by square root of 3 divided by 1.25 divided by 10 power 3. It works out to 65.21 kilonewton in the single shear. Whereas now I want to calculate what is the kb value. Therefore, as per IS 2007 class 10.3.4, just now discuss these formulae, substituting into these formulae. What is kb? Therefore, kb from the first criteria 39 divided by E divided by 3 naught is equal to 39 divided by 3 multiplied by 27. It works out say 0.493. The second criteria P divided by 3 naught minus 0.25. 60 divided by 3 multiplied by 27 minus 0.25 is equal to 0.49. And the third one is equal to FUB divided by FU. Say 400 divided by 410 or 0.975. The last one is 1. Therefore, out of all these, the first from the second criteria 0.49 is the minimum value. And the second one is equal to the thickness for the bearing, right? Here you please see that the thickness for the bearing from this schematic student, either the thickness of this flange or the thickness of this flange is equal to 11.6, or this thickness of the gusset plate is equal to 16 mm, and the thickness of this gusset angle is equal to 15. Therefore, this 15 or 16 or 11.6. Therefore, this 11.6 will fail in bearing. Therefore, T is equal to 11.6. That is what I have just concluded. Hence, the design bearing capacity of the bolt VDPB is equal to 2.5 multiplied by 0.49 multiplied by diameter 24 multiplied by thickness 11.6 multiplied by FUB 400 divided by 1.25 divided by 10 power 3. It works out to 109.13 kilonewton. Hence, the bolt value. Next subheading is what is the bolt value. Therefore, the bolt value is the least of these two results, right? Hence, that bolt value will now work out say 65.21, not that of 109.13. Please make a note, right? Once again, this bolt value, student, now what is already given in the problem is the I'm just assuming, because nothing is given, assuming the ends of the column are cut by machine and flush. They are provided and flushing the base plate, right? Even the top surface of the base plate is also cut by the machine and flushing. The column end is flushing with the slab base. Therefore, there is a perfect contact between these two. For entire load will transfer to the bearing only. However, now there is no load to be transferred by the gusseted system, but nevertheless we will assume that 50% of the load will be transferred only by the bearing and remaining 50% by the gusseted system, right? Otherwise, there is no load need to be transferred by the gusset system, right? That is then we cannot provide how many number of bolts that, right? Hence 50% of the load need to be carried by the gusset system. Hence that works out say 850. Therefore, the number of bolts that we need to provide n is equal to load to be transferred by the gusset system is equal to 850 divided by the bolt value 65.21. Say 13.06. R say will generally providing in 2 rows, hence R say 60 number of bolts, right? 60 number of bolts. R say hence provide 8 24 mm dia bolts in on each flange in 2 rows as shown in the figure. As shown in the figure, right? Now I'm showing this figure student like this, right? I'm providing right here 4 plus 4, right? Therefore 8 connecting the gusset plate as well as the gusset angle. Actually this is common area, right? Common area, whereas this is also connecting the gusset plate and gusset angles, right? 4 plus 4 8, therefore 8 plus 8 16. That is how I'm providing in 2 rows here, as well as I'm providing these more 8 in 2 more rows as shown in this schematic. And also provide, say because there is no tension acting on the base plate, nor it is subjected to this column is subjected to a bending moment. Therefore we need to provide just anchor bolts which will be connecting the base plate with that of the gusset base system with that of the base plate to that of the pedestal, concrete pedestal like this. Therefore say provide at least 4 20 mm anchor bolts, right, on 4 sides of the gusseted system as shown in the figure. Now let me show this schematically. This is how just I'm providing student, right? Just how told that these are 8 and these are 8s, right? This is how the design. This is how the design are. Even it looks like this, right? Therefore, right, in plan, right? Therefore, those 8 are here, right? 1, 2, 3, 4 here, not 6, right? Not 6, right? 8 and these 8, right? Or this is how in front elevation it is looking like this, right? Or the 3D schematic. Or if I see the figure, right? These are the bolts, at least, right? 1, 2, 3, 4 anchor bolts. 4 anchor bolts like this, right? 1, 2, 3, 4 anchor bolts. That is all the design of a bolted gusseted base, right? That is of the design, student. I hope you enjoyed the discussions what we had in today's class. Therefore, if you have really enjoyed the discussions, right, don't forget to click like, share, subscribe to our YouTube channel. We'll meet in the next class with the design of a welded gusseted base. Till then, bye bye students.